Now I just wanted to show you a similar thing that we did previously with the web editor. So retrieving just a single pixel and looking into the data and trying to understand the behavior of the data over time. Again, we start with importing the necessary libraries. We connect with the backend. We select the temporal extent that we're interested in. In this case, we use 1 year between 2018 January until the end of the year. We have just a single point for this example, which is located somewhere in South Tyrol. And yeah, this is just an example, but in theory, you could even have multiple points, and that could be quite useful for use cases similar to the one that Alex presented before, where you want to train a machine learning model. You already know where are the locations of the training pixels, and you want to retrieve the data. And OpenEO eases the process a lot, because you just need the points and then you get the data out of it, and then you can train your model by yourself with the data that you just extracted. You won't have to download a bunch of Sentinel-2 tiles or Landsat or whatever. So you just need your coordinates, and then you can proceed with your work. So we just create some variables with the coordinates. Again, we use always the same collection. We use again the RGB bands and the cloud mask. We do the same thing as we did before to filter the clouds. So we apply the cloud mask to the data that we load with the load collection step. And here, as I was doing before, we create this cloud mask, and then we apply it to the data. We then apply the mask, but just not at all the bands, because here, for example, we loaded the RGB plus the cloud mask. But since we are not interested anymore in the cloud mask before applying the mask, we just select the bands that we are interested. This is to show you how it's easy to pipe different OpenEO processes and to, let's say, slice the data, recombine it. Here, there's not an example, but it's also possible to load Sentinel-2 data, Sentinel-1 data, and combine them later. So it's quite powerful and flexible as well. So we can download the data as an SDF, as I was showing before. And if we open it, we would see that we have the 3 bands that we requested. It is just a single pixel, and we have 92 time steps. Now we can just plot it, and we may see that something went wrong, because ideally we shouldn't have these spikes in the data if we masked out the cloud. So probably a cloud mask that has been generated for January 2018 wasn't perfect, and that's why we are getting these such high values here. So to look at the behavior of the signal in a, let's say, more efficient way, we can just try to apply a manual threshold, and we would see that the signal increases over the vegetation period, and then decreases again during the winter months, because here in Europe we have summer in that period, and not like you, that you have it reversed. So you would see it like mirrored if you would look at the data in South America, for example. Now let's try to just, instead of downloading this data, I would like to just create a batch job. Let me just quickly copy and paste a code snippet that I have here, because I want to show you another cool feature of OpenEO. So basically, if now I have to create a job which is called like this, and I create it, Just wanted to show you that now we interacted with the backend with this Python client, but also the web editor is an OpenEO client. So if we go back to our OpenEO editor instance here, in a while we should see appearing here this job that we have just created. So let me just refresh the page maybe. And this is quite interesting. Yeah, here it is, this Sentinel True Data Mask. This is quite interesting and useful because on one side you have your Python code, on the other side you could use this web editor to keep track of your current processes, the status, and so on. Those are all things that are also available on the Python client, but here instead it could be much easier to directly see the status, and you can even download the results that have been generated, let's say, with the other client, because they're both present on the backend and they can be accessed by either Python, R, JavaScript, and so on. One last example that I wanted to show you before giving back the word to Alex. Alex talked about UDFs, so user-defined functions before. And on the OpenEO website, if you go to openeo.org, then under user documentation UDFs, you would see and find a description of what UDF is being, what's the meaning for a UDF for the OpenEO API. It means user-defined function, and it is basically trying to fill in a gap where the OpenEO processes, where an OpenEO process is missing, because maybe you would like to apply your fancy regression model that it's not yet defined in OpenEO, or it cannot even be defined because there are plenty of machine learning models, so it's not possible to have everything defined in a standard and common API. So this is why sometimes UDF could help you to basically construct your workflow with the current available OpenEO processes, and just for the last step, apply this user-defined function. Now, I want to show you a simple example that leverages R code within our backend. And it seems, wait, it's not this one. It is this sample RUDF here. So again, I'm starting with the load collection, always the same. I'm loading some data. This is the area of Finchgau. It's a valley in South Tyrol where there are a lot of apple orchards and vineyards. So I'm selecting this area, which is covering some fields like the river and also an urban area here. I just save it. We also have some bands. Then I just take the median over time because I want to apply a machine learning model. Let's say a model that has been already trained with some data. I just want to predict the classes using this particular model that has been trained. This has been trained with R. And now I want to apply it using the OpenEO interface. So inside this reduced dimension, what I'm doing, I'm calling this run UDF process, which takes as input this URL. Just want to show you the content of this URL, which is an R function. And basically what it does, it gets an ML model, which has been already trained, it loads it. And then the actual function takes the data as input, given the preloaded model, computes the classes, the prediction, and then returns the result. Let's go back here. Yeah, the runtime, basically, it is R, it's not Python in this case. And then, we apply this on the bands because the model takes as input the bands that I've selected, so red, green, and blue, and near infrared. And then at the end, it saves the result as a GeoTIFF. So as I was saying, ideally, we shouldn't need any UDF, because if all the processes that we would need are already predefined in OpenEO, already available, tested, and so on, no one should use these UDFs. But this case is not ideal. There are plenty of things that we would like to try on the data, and maybe we don't have the processing power to do it locally. We would like to do it in the cloud, and this was our approach to it. As Alex said, there could be security concerns, because if you run some malicious code in this UDF, you could do something bad on the backend. And that's why ideally the running of the UDFs are in a separated container, so that they cannot interact with the live environment. So this would be the result of this UDF. And I can't tell much about the meaning of the classes, but we can see that basically the river has this 14 class, probably it's water, and we can see some fields that are different. Maybe one is apples, the other one is vineyards. The meaning of the class is not important. I just wanted to show you that it's also possible to apply custom R code in this case, and probably in our backend not, but in other also Python code.
Okay, then we come to the second part. So now you have seen a little bit how OpenEO works in practice, how the clients look like, how to use them, and even that you can combine things. You can really see the clients as different views to the same database of jobs and processing. And now we can go over to the applied part in the SAR domain and the SAR2CUBE project. So this is now the second half here, so a little bit of a background of how we defined our SAR data cube so that it works with OpenEO, some of the basic operators and SAR-specific operators that we set up, and then also some application examples and how it works. So this is just to again, a view to the past, old data sets that we had to generate for this previous project that I mentioned initially, SynchroMap. There, whenever we wanted to look at things like different filter sizes for your multi-looking, or the window size of your coherence window, then every time you have to realize physically this data set and store this, and with every time you store a different filter size, it also occupies space on disk. Then if you want to work both in the SAR geometry or in a projected coordinate system like UTM, then you have to store this twice. So these numbers add up fast. When you use small filters, then there's not a huge difference between the one. The larger the filters become, then there can be quite a large difference here. That is because here we have 4x19, that's approximately 80 meters per pixel squared. And if you then bring this to, for example, Send-2 grid, which has 20-meter resolution, and then it's of course 16 times more data basically that you need to store this. So this can become quite expensive to store projected data. And it might be much more convenient to be able to work and store only the SAR data in your system. This is basically the take-home message from this slide. So, but for this, you also need to have a data model and a way to flexible do the conversion from SAR to geographic domain, which usually takes some processing time in order to achieve that. Then we come to how we also beforehand represented our data in coherence. So coherence, as you know, is basically the stability of the signal between two observations over time. And then you can calculate this between any two SAR observations that have been co-registered. And we are looking here at the coherence amplitudes. So only the real part of your complex number, basically. And then we can do comparisons, and the longer the time between the two observations, especially in vegetated areas, the less coherence you will have. You can see this here that over time, so in this first image here, you see this is 12 days apart, and then this is 24 days, 36 days, 48 days, and 60 days apart. And basically after 60 days, the only thing that remains stable is urban areas or bare rock. This is how coherence works, basically. And you can also follow along the shortest baseline, so you can compare the coherence between images next to each other over time. These are the ones here on the diagonal, and then you can see that the pattern changes based on the season. And again, here in end of winter, beginning of spring, there's still quite a lot of coherence because vegetation is relatively stable because it's not growing. But then when spring sets on, then it becomes less and less coherent because the vegetation is growing, and then between two observations, the change in the leaves and twitches and so on is too big to have any level of coherence. And you can do this for all the combinations, but again, you need to store all of them, which is quite a lot of data. And of course, you have this also in Sentinel-1 in this example in the two polarizations, so FEV and VH. And this also changes a little bit. So for this, initially we set up a data model then to keep all this data, which we set up also in our data cube in raster. So this is now actually a 5-dimensional data cube, because now you have basically this, what I just showed you, this matrix with 2 time axes. And then inside each location, you have the spatial information of each individual data set. And then as the 5th dimension, you have actually your feature space, so the VV and VH. So just to show you that these data cubes are not always necessarily only 3-dimensional, but they can be also more dimensional. So you have kind of a grid of grids and then the feature space. And this makes our 5-dimensional data cube. And even for just a very small study area of this example here, so this area here is exactly 1000 by 1000 pixels. And if you store just for the small area, one year of data, that's already 6 gigabytes, and a full scene of Sentinel-1 data in this domain would be in the multiples of terabytes, actually. So this becomes very expensive to store all of this data in the long run. So then we had to come up with a different data model in order to deal with this. So the first thought that we had was, what is all the information that we need to generate all these data products from SAR data? And this must be what is the basically the trade-off between pre-processing and storage space that we have. And then for SAR data, we want to keep the data in the complex geometry, in complex data format, so that we can derive all the products. This means also the interferometric products based on the phase information, but also all the data that is based on the amplitude information, like the coherence amplitudes or the intensities and so on. And then as coordinate system, we have our sensor observation geometry along azimuth and range instead of the geometric coordinates along latitude and longitude or east and north, or whatever the axis of your coordinate system are labeled. And then we have a full time series of these observations for each overpass of the satellite when they come. In the case of Sentinel, this is every 12 days, and then there are 2 satellites in the constellation. So every 6 days, you have a repeat pass geometry where you have the satellite at the more or less exact same location. And these are the ones that we stack then together as our data cube. What you need to do then is to do co-registration of this stack to a master image. As you might know, when the satellite flies, it's supposed to have almost always the exact same path, but due to some disturbances in the Earth's gravity field, it's never exactly at the same location. There are some small variations, which is the so-called orbital tube. Basically, that's kind of the the delta E around your orbit trajectory where the satellite flies, and you need to correct for the small differences there and co-register your observations so that you have a perfect aligned stack of images, basically. So this is the image alignment, and there might be some radiometric differences due to degrading in the sensor changes in the ionosphere, which might have a small impact on your signal, and so on. So you need to do a radiometric calibration of your images, and then in some sensors like Sentinel, you also need to take care of the fact that your actual image is actually already a mosaic of a number of smaller images, which are divided by so-called subswath and bursts. So you need to also take care of remosaicing together your images into full observation scenes of the overpass track, basically. And then, of course, you need to take care of both polarizations, so both observational bands that you have at your disposal. And this is basically the minimum that you need to derive everything for the amplitude part of the signal. And then there's also the phase component, which is required to work on INSAR applications. And for this, you need to correct for differences in the topographical phase based on a specific DEM, the one that you want to use in your area, basically. And this is also something which changes every single image. So you have basically another band of information that you need to add to your polarizations, which is this topographical phase component, which is needed to then later generate all the combinations of interferograms that you want to do. And finally, the last part that we are missing is the information on the translation from your sensor geometry into a geographic coordinate system. For this, we found a way of kind of defining a transformation once and then generate a lookup table where for each pixel you have a fixed linear formula, basically to do the translation relatively efficiently, and then on the fly you can transpose from your sensor observation to the real geographic orientation of your scene. That's kind of the data model that we have created there. And when you have all of these pieces of information, then you can generate any SAR product based on simple mathematical formulas, basically, which are just trigonometric functions, plus, minus, divided, some indices, and so on. So really no fancy math needed anymore after that. Then you need to put all the data in the cubes. We did this for a number of different study areas for our project. Again, here, another thing that we also wanted to check out now is look into the effects of the different sensor geometries in ascending and descending orbits, and possibly also different incidence angles depending on the location of the subswath over your area. And also these study areas are located in completely different biomes, actually. There's an area in southern Spain, south of Sevilla, in Doñana National Park. It's a wetland and agricultural area, super flat next to the sea. Then we have South Tyrol, which is a very steep terrain, deep valleys, high mountains, lots of topography, which is, of course, quite difficult for SAR applications due to effects like foreshortening and layover and so on. And then we used the Finland study area in Finland, which is a complete different condition. Long periods of wintertime, frozen conditions. So that means the period where there's high coherence is much longer, because in frozen conditions, vegetation doesn't change a lot, and allows for a lot of interesting applications also in, for example, forestry. That might be less relevant, though, in Argentina, I can imagine, because it's probably not so highly probable that you have overfrozen forest for several months in your area. But still, was quite interesting here. So then the standard operators that we needed to have are basically the same that we saw already by Michele in his exercises and actions. So now we want to be able, still like before, to do slicing in time to get a time series of a specific location. We do want to do spatial slicing to get subsets of a specific area. Then we want to do standard SAR operations, which are basically kernel operations like multi-looking to reduce the impact of speckle in your scene, and of course the geocoding card to bring the data to a different geometry. Here it's quite important that when we define these lookup tables for going from SAR geometry, we also this actually works also the other way around, so that when you select a point, you can put your coordinates in, for example, lat long, if you have a lat long reference grid defined, and then you can get the data still in SAR geometry, which is actually advantageous because every kind of resampling that you need to do on SAR data will actually degrade the quality of the signal. So sometimes it might also be an idea, instead of working in your projected coordinate system, to bring your reference data into the SAR geometry and then do the classification there, or the analysis of an individual pixel or something like this. And that's what this metric allows you, because it actually goes both ways for the translation. So you can then also do your whole image analysis in this geometry if you don't need to involve any other sensor data, for example. Or in the most extreme case, you could even consider to reproject your Sentinel-2 data into the SAR geometry. Not sure if this looks very nice anymore then, but at least it would be possible. Try that. Then we go over to deriving the classical measures of that most of you are used to. Most people who work nowadays with SAR data, especially in the big clouds, they are actually only used to having the backscatter in form of intensity available, because in the Google Cloud or also an Amazon Web Service, you will not find the single log complex data. So you can only work with the amplitude data there. The reason for this is simply that unless you have not solved all these issues that I presented you before, it's very, very expensive due to the amount of data that you need to take care of and the processing that you need to do to work with the SLC data directly, due to simply their size. So probably 7-8 times more disk space, and then if you want to store interferometric products with all the different temporal combinations, you basically have a quadratic growth of data. That's why the big clouds so far have avoided to provide SLC data and these more interferometric processing capabilities. Here, then it works the same as before, like in the web editor that Michele has shown. You can put your simple formula for the intensity here, and then we can generate the graph, which is really the mathematical formula, as you can see, for deriving. This is just the square of the real imaginary part of your complex number, and then getting the root of this. So mathematically, this is nothing fancy, and since all the data has already been prepared the way I presented before, this is also a very cheap operation to do on the cluster. It's a very simple graph. We can do the processing. This looks a little bit more complex now because we need to take separate care of and Michele will show it to you later. But all you have to do here is then put your formula in there and into the reduced dimension function as before. Then you can select your multi-looking size that you want to work on, and finally geocode your data and retrieve your result as an image or as a geotiff or an LCDF if you have a time series. And finally, you can look at your nice SAR image again over the area here in South Tyrol where we are located. The optical data that Michele showed you in his last example is somewhere here in this area where my pointer is right now. So you can see we have really quite topography prone area here, which means that it's not always very easy to deal with SAR data, and you have a lot of shadow and overlay area which you should exclude from your analysis when you work in such mountainous terrain. Because for these you cannot even correct them with the terrain flattening anymore if you don't have any information there. Then the next thing is, for example, calculation of coherence. Again, coherence is also just a simple mathematical formula. And then all these products, for example, different multi-looking, we can just change the number in our graph and on the fly generate another size. And the processing of such a scene, this is now really a full Sentinel scene, is less than a minute, so it's quite fast actually for even for relatively large areas. So these are several hundred kilometers in width and height, so that's quite a large area. And yeah, 3x15, relatively high resolution, 4x19, a little bit coarser, depending on the number of looks that you put in there, depending also a little bit on the application. And finally, the interferometric part, so that you can also derive the interferograms. This last part, there's still some problem in our processing chain. So right now we have this not fully implemented in OpenEO yet, but that is pending and soon will be available as well. We did, with a little workaround, run it on our cluster anyways, so that we could test the performance of it, but without launching it through an OpenEO process, just directly through Python. Basically, we still need to hook these up as a process, basically. One thing that you can see here now, as long as you work with an individual scene, you can work with a normal kind of workstation machine, 8 core, 32 gigabytes of RAM. And for some of the tasks, like the multi-looking, which is a very simple operation, this is the same in our framework, SAR2CUBE, or Snap, the toolbox from ESA, which you might know. When it comes to a little bit more complex operations, like for example, the calculation of coherence, then it's already quite a bit faster when using the SAR2CUBE framework due to the parallelization of the code. And then where it really shines is because of this X-array Dask backend that we have, we can just pump up the resources, add more virtual machines or make bigger virtual machines, and then we can compute full stacks of images. For example, all the interferograms of the shortest baseline over a year, which is 60 images more or less, and we can compute them in just 2 minutes or so, or do the geocoding of a full stack of images for a full year also in just a minute. This is because it scales with the number of cores and RAM that you give your processing engine, and that is something which a desktop software like Snap cannot satisfy. This only scales to up to 8 cores, but not more, and it cannot deal with more RAM either. So then you cannot get any faster. So you can really benefit from the large number of cores, so you have more than linear speed up than when you can augment your resources. Here you can see some examples of these data sets also. So for our terrain motion, here are the generated interferograms from our software, from SAR2CUBE, and here are the ones from a commercial software from a company that we have worked together with in this project, Daris Technology. And then we just compared basically the interferograms as they come from there and from us, and you can see they're very similar. In order to prove this further, we did also a persistent scatter analysis over our city here, which is a technology for monitoring sediments. So here you basically trace the stability of a point over time, and for each point you can plot the movement between 2 subsequent observations relative to the displacement of the wavelengths, which is coming from the phase observation basically. And so you can even observe very small movements in the sub-centimeter range from space observations, basically. And yeah, points that are moving are depicted here with a deformation per year, basically. So yellow area here is where slowly subsiding, and green areas are basically stable areas. So we are living luckily in a relatively stable city here. And this was again comparing against the software from them and against SAR2CUBE, and you can see that the trends of this curve and the magnitude are very similar. So someone who would do an analysis would come to the same conclusions, and this was the most important for us. Then just to give you an idea, how does it actually work for mapping exercises? What's the information that you can get of this matrix of coherence that I've shown in the beginning of the second part. So we have here again a terrain with different land cover types. These darker areas are actually forested areas. There you expect very low coherence. The white areas are urban areas. The black areas are rivers and highways, and then the mountains with the higher part bare rocks and open space. And here on the rock faces, there you see the vegetation. Here you see also the issues with the terrain. These lines here, this is because from the sensor geometry, the satellite cannot see this. It's actually in the radar shadow, so there's no information available for these areas. That's why it's so important that you apply also some kind of mask when you do your analysis when working with this SAR geometry data. And now for each of the locations here, we actually do not have just this 2D image, but actually for each location, we have a full matrix of values which come from every single coherence pair that I've shown you before. And based on the land cover type, they have completely different patterns over time. So if you think about the urban area, this has a very high coherence of near 1, no matter the distance and time between two observations. That's like super stable. If you think about a water body, which is always in motion, this is the complete opposite. This has always a very low coherence with a value near 0, no matter if the observations are directly next to each other or years apart. And then any kind of vegetation depends a little bit on their status. So in this case, for example, you can discriminate a natural forest, which is this pixel here, from an orchard because of the management practices. The natural forest has always a relatively low coherence, though higher than water. So the average of this is higher than this. And the orchard, which are also trees in the end, right? But these are managed trees which are cut back in specific periods, for example, over winter time. That means over winter time, you get actually quite a stable signal from a managed forest, because here all the trees are cut back, and you have the bounces of the illumination from the SAR signal coming always in the same way, because they're just reflecting out of the stem. So you get quite high coherence during this, and then this kind of different information over time can be used to train a classifier to derive different land cover types, from which you then can generate a land cover map just based on the information of coherence, which is actually quite accurate. And then you can see all the different classes: artificial, surface, arable land, vineyards, pastures, bare rocks, wetlands, inland waters, and so on, just based on profiles on the type of land cover that is there around, basically. So quite a powerful tool. And similarly, if you read the second paper that I presented in the morning about crop type mapping, there they also use this kind of temporal variation to look at which is a mixture of the conditions in which crop grows, and the management factors is basically give you different time series along the shortest baseline here, which would be the diagonal in the middle. And that you help to discriminate also between like sugar beans and maize and corn and tomatoes and whatever, basically. But you can also use it just for normal land cover mapping. So recently we have been able to, since we now have this all running on the large infrastructure, to do this mapping not just for small test areas, but for our whole province and region. Or as I said before already, we can do this crop mapping. And this is really crop mapping with not just 3-4 different crops, but crop mapping with 20 different crops or so. So that's actually quite a good instrument to do this. Of course, this works here in this study area quite well, because it's a super flat area. So there you have no issues with the SAR geometry, actually, like in our mountainous regions that I have shown you before. Then we used also other applications, like, for example, windfall damage from storms. We had a big storm about 4 years ago here in the region, where large parts of our forest have been thrown down. You can really see these areas. They're really extensive. And a lot of timber had to be removed from the forest afterwards. But with optical data, the damage assessment was almost impossible because the storm occurred right on the onset of winter, which meant that the images were either cloud covered, because during this period here weather is not so nice, or then simply the snow came, and then you can also not see any difference anymore on the ground. So we were looking if with SAR data we can actually do this mapping, even though the weather conditions are less than optimal for doing any kind of analysis with remote sensing. So we started this research activity. In the end, our forestry service, to have a quick evaluation of the mapping, they had to do helicopter flights and more or less manually do the cartographic damage assessment of this. We hope in the future we can support them better, because now we have implemented this also based on SAR data, and what we did here is basically run harmonic models for the time series of each pixel. This is here the backscatter now, the intensity, where in the case that the forest has not been damaged, we would assume a harmonic curve going basically with the seasons over the years. But in the case of a change of the land cover, because the trees have fallen down, we can then see that our prediction based on a trained model and the reality do not fit well together anymore. Then we can see these deviations from the actual model, and this can be used as an automatic mapping approach for finding all the area that has been damaged by the forest. So as a conclusion, in the SAR2CUBE project, we have set up this processing chain based on actually open source again completely. So the pre-processing has been done with the Sentinel toolbox, but only up to the level to generate this SLC co-registered and calibrated stack with reference faces. Then we have indexed this into our data cubes, from where on we then were able to apply all the processes and processing engine that we already had for OpenEO by just coming up with process graphs that do the calculation of the kind of products that you need for SAR data. So the coherence, the interferograms, or the intensities. And then finally, these are again available through the clients that Michele has shown you for any kind of application, be it persistent scatterers, land cover mapping, change detection, crop type mapping, everything that one can imagine. And yeah, the most important thing for data provider is that this is relatively storage efficient, because you just need to store one time series of your preprocessed SLC data then, and can make this available. So this would be I would call it analysis ready complex data cube. On this you can then do scalable processing and do any kind of analysis. Now, for the future, actually, our goal is to implement also the SAR2CUBE infrastructure into a backend that has the SLC data available, not only for our study areas here in the Alps, but on a more global level. So we hope we can do that soon, so that this is also available to anyone who wants to do this. Nevertheless, again, if you want to work with this or play around with this, this is all open source. This includes both the pre-processing part, but also the whole OpenEO part. It can be set up also locally then, and then it would be interesting to work also on some more examples of more challenging things, like doing the PSI directly in OpenEO, SBAS, offset tracking, all the things that people typically do with the interferometric SAR data. Could also be thinking about more telemetry-based applications, and so on. And of course, also tested with other SAR centers than just Sentinel. Could be also to work with Cosmos Sky, Terra X, SARcom, or the other SAR missions that are out there, Radar SAR. Many to try yet. Of course, then you need to always adapt the pre-processing chain a little bit based on the particularities of each sensor. And finally, we work also on the standardization of this metadata under the COS card for L. group, basically, for defining them for in SAR also. Yeah, that would be everything from the presentation part and from my side. So thanks a lot for your attention again. I hope also this part was interesting for you. If there are any questions, then feel free.
Thank you, Alex. Wow, it's really impressive job. Yeah, actually, when was it? When Valerie presented on Tuesday, Valerie Pasquarella, and she presented a lot of change detection applications in Google Earth Engine and for optical data. And one of the questions was about SAR. And so here you have answered that question like extensively, I believe. Really cool. One of my questions that just to confirm, for all these pre-processing steps for SAR data, you are using these SAR scripts or scripts SAR that Michele shared?
Yeah, I mean, for the pre-processing, we use the Sentinel toolbox from ESA for parts of this pre-processing, but this is also open source, so everyone can have that. Yeah. And we have in the SAR scripts Git repository, there should be the graphs that we used for do the snap processing, so that the pre-processing, everyone can follow this. Oh, Michele shared the link on the chat here also. So we have all the, so that you can reproduce the same kind of SLC layers that we have for as an input for our data cube, basically. That is the first step, and then after that is the setup of the OpenEO on top of that. Basically, okay. Exactly, but you can do this then for any area in the world where you have downloaded the data basically yourself.
Yeah. Good. Are there any questions here for SAR people? I'm like more like optical people. ¿Alguien trabajando con SAR acá? Uy, te miraron. ¿Tenés alguna pregunta? Ok. ¿Alguien más? En el chat, si los que están, las personas que están virtual tienen alguna pregunta, por favor, avanti, la pueden escribir en el chat. Ok, también ahí están los links para quienes les interese.
By the way, I can also later send you the presentation, then everyone can get a copy and just, you don't need to scribble down all the links now by hand. I will send it by email to you later.
Yes, I would appreciate it. Yes.
And this is, since everything else we do is open source, you can of course just put this online or share with everyone. There's no constraint of sharing this. There's nothing secret in there, so it's fine.
Yeah, that's very good. Okay. Then if there are no questions, maybe Michele, you can start with your part. Thank you again, Alex. It was really interesting.
Thanks again for having us.
Yes, should work. So as you've seen from the presentation of Alex, it's a lot of stuff. So there was a lot of work for being able to actually have this Sentinel-1 SLC data in the data cubes. It wasn't something straightforward. We had to come up with some new ideas, but at the end we managed. And basically what we are doing, as Alex said, we are pre-processing the data. So the Sentinel-1 data, it's pre-processed using the ESA SNAP toolbox, which is freely available. And later on, the whole data set is being indexed in OpenDataCube. And after this step, we use OpenEO in the same way as we do with optical data. However, since this SLC Sentinel-1 data is not geocoded and it's not on a regular grid, there are some operations that cannot be done in the same way as we are doing with optical data. For example, we cannot just retrieve some data that is within a bounding box that we define, because the data is basically each pixel of the original data has a coordinate which is associated, but it's not on this regular grid. So you firstly have to look on the coordinates of each pixel and then try to get just the ones that you're interested in. I'll show you how to do this using again OpenEO in this example notebook. This is again on the repo that I've sent you before under Eurac OpenEO examples Python. And now I'll start with the SAR2CUBE OpenEO examples intensity. So here I put some useful links, the SAR2CUBE project webpage, where we just recap some the most important things that we achieved in the project, and also the various conferences that we attended and the various presentations. I think that after the introduction that we gave you today, we could also insert it here in the various conferences and presentations. Again, I'm repeating where you can find the OpenEO Python plan documentation, the Getting Started guide, because it's always something that can be useful. So the topics will be, you already seen that before, but again, log in to the Eurac OpenEO backend containing the SAR2CUBE datasets, discover the data and the processes available, the ones specific for SAR, the SAR domain, access and process data via OpenEO processes. The OpenEO processes will just try to compute the intensity of Sentinel-1 in this case. And yeah, then we'll see how much time remains. So just to remark this point, always check the OpenEO library version that you have. You can do this by checking the version like this, and also checking the one that it's available online, so that you're aligned with the latest features that are available. And just importing some utilities functions that include like the mapping widget that you'll see afterwards. Again, we are logging with the backend to interact with it. We are authenticating. This thing I haven't shown before, but basically to check if you're actually authenticated, you can use this .describe account. So for example, if we wouldn't authenticate, we would see that this won't work because we are not authenticated, and it's not able to retrieve the account information connected to OpenEO. So this would be my account with my name and user ID. So as I was saying before, you can list all the collections available on Eurac in this case, but it would be the same on our backends. And if I type SAR2CUBE, I would get all the collections that are being indexed with this name. This is just useful because I can, let's say, know what collections have to be processed with the, let's say, SAR2CUBE pipeline compared to data collections that are being stored and can be indexed in the classical way. For example, we work with the data over Sartiel or our region, but for another project, we also index data over Finland and over Doñana, Sevilla in Spain. For example, if we look into the ascending track of Sartiel, this is because the Sentinel-1 satellite passes over, basically it has different orbits, and depending if it has the ascending orbit or descending orbit, I mean, it generates different data sets. So then we have to index them as different collections because there are some particular features of each orbit. So, for example, the shadow, layover, foreshortening effects that are related to that particular orbit, and that cannot be applied to both of them if there is no, let's say, terrain correction or terrain flattening involved. So we would so the area that we have indexed is covering South Tyrol, sorry, mess, and which is here in the north of Italy. The temporal extent that data that we have available, it covers time between end of 2016 until basically now, a week ago. And here comes the complicated part. The SLC data is complex. So not because it's complex to process, but because it's actually composed by complex numbers, so real and imaginary parts. And when we started the project, there was no way to index complex numbers in OpenDataCube. So what we had to do was basically to split each image into a real and imaginary band, so that we could index it as normal floating point numbers, and then later on recombine them with the OpenEO processes. So you would see that for each polarization, for example, for VH here, you have the real and imaginary part, same for VV. Then we also have the interferograms indexed, which we won't use right now. We have the DM, the digital elevation model. We have the local incidence angle. Those two layers are particularly useful to compute the areas that are in shadow and for being able to filter them. And the most important thing here is the grid_lat and grid_long bands or layers, which contain the coordinate information for each pixel. Which is what I was saying before. So the data which is in the data cube is not on the regular grid, but it has this coordinate information which is attached to each pixel using the information from another band. And this will be used at the end when we want to geocode the data, so transform it to a regular grid and reuse it with softwares that we are used to use, like QGIS. We also want to visualize it, combine it with other data sources that are on regular grid. This is the extent, and reference system, it's not real, because in order to index the data in OpenDataCube, you're forced to assign a reference system to the data, and this is basically just a fake reference system. But I mean, this is just for your information. It's not related to the next steps of the processing. In the processes, as I was saying, there's one, the geocode process, which is the one that is more interesting. So basically, it geocodes the SAR data, given the SAR projection and resolution. We have chosen to allow just 10, 20, or 60 meters as a resolution, because the aim of the project was to combine data, the SLC data from Sentinel-1 with Sentinel-2. And since Sentinel-2 is either in 10, 20, or 60 meter resolution, we just fixed these kind of resolutions. But of course, this would allow you to re-project the data later on in a second case. Okay, so let's actually start with an example. Here I'll show you all the necessary steps to generate the intensity. Maybe I'm not sure if I'll run it because it takes a couple of minutes, but anyway, with this widget, we can replicate basically what we were doing in the OpenEO web editor. So with Jupyter and these widgets, it's really more interactive than just writing a Python script and executing it. We can actually interact with something like this map. We can have a background layer deactivated, activated, and so on. This, in this case, is just to get the bounding box that we are interested in instead of typing the coordinates manually. And subsequently, we are again starting with this load collection step. We use this Sentinel-1 level 0. We call it level 0 because it's not the original SRC data, but it has been co-registered between a master date that we have chosen between basically the end of 2016 and now, so in the middle of was 2018. So all the data is co-registered to a single master date, and there are some pre-processing steps. That's why we call it level 0. So this is L0. It's orbit number 117. It's a ascending orbit, and the data is over SAR2. Here I've selected the month of June 2022, so just a couple of months ago. And I'm running the load collection process. Then this is really nice from the Python client. You can create mathematical formula quite easily because you don't have to drag and drop processes. You can just write it as it would be a normal NumPy computation, for example. So, for example, we can refer to the real VH band and to the imaginary VH band, and we can just combine them like here. So we just take the power of 2 of both, and we sum them, and the final result would be the VH intensity. Since this would translate into a reduced dimension process, then we have to do this dimension step, but it's not so important here. After that we have computed the intensity, we should compute the multi-look. So this is not an operation that you have to do all the time because you could apply also different kind of filters, but the multi-look is, let's say, a kind of standard operator of SAR processing. And here it is well explained by ESA. Taking this picture from a PDF from them, and basically it shows you what's the size and the shape of the original SLC data, which is this one on this size, and the dimensions are range and azimuth. And you see already that a pixel is not covering an equal area, so therefore we have to do some kind of processing to adjust what a pixel contains in terms of spatial coverage. And the multi-look helps us, the multi-look is basically just a window operation. So you define a window, which is, in this case, it's not a square window, but it's a rectangular shape. And performing this multi-look, you would more or less you would get this result. You would refactor the data into something which is more meaningful for us to look at. How we translated this multi-look into an OpenEO process. The OpenEO process is called aggregate spatial window because what it does, it performs this window operation over blocks of data and computes aggregates for them. The operation that you use for aggregation, in this case, it is just a mean. This kind of syntax for the OpenEO process is not, let's say, the official one. I mean, it works, but since this process is still experimental, we don't have, let's say, the clean way of referring to this process. Because, for example, you see here that if we do reduce dimension, we just have to call reduce dimension and give some parameters. Here, instead, we have to refer to some kind of internal objects with a callback. So this is just because it is still not officially implemented in the OpenEO API. Because you might want to know how new process in OpenEO comes in. Basically, if someone wants to define a new process, it has to draft it, it has to implement it, but to become part of the official OpenEO API, it has to be implemented in more than one backend. So since we are the only one having this process right now, it can't still be part of the official API. But hopefully we will solve this soon once we will be able to implement this in OpenEO platform. Yeah, after that we have computed the multi-look. We have more or less a squared image. We want to get the average over the temporal extent that I've selected. And then afterwards, I just rescale the data to get a PNG visualization. Here it took around 3 minutes, so I'm not going to write. I already have the data downloaded here. And you could directly see here the difference between the original SLC data on the left side, which is stretched out, compared to the multi-look version, which is on the right. This is still not geocoded, so the distance between the pixels here is not regular, so it's not 10, 20 meters, so it is slightly different. However, in the next step, we will pass from this kind of data to the geocoded version that you can analyze in other kind of tools. So this would be the geocoding step. Again, we are just doing the same. We are loading the data, we are computing the intensity. Again, we apply the multi-look. Here, additionally, we want to convert the data from linear to decibels, so that it is easier it's easier to understand what we are actually looking at, because converting it stretches out the values, and the visualization is much easier to understand. Here we have the first step that is requiring this latitude and longitude data. Because to geocode the data, we need the information attached to each pixel, so the latitude and longitude values of each pixel. We have to perform the multi-look also on this data, because when we want to geocode the data, we must have on one side the intensity values, which has, let's say, X times Y shape, but also the coordinates on the other side that must have the same shape, because each pixel must correspond to another pixel. We use the merge cubes operator process to merge the intensity and the coordinates grids. We take the average over time, and at the end we geocode the data. We can set the resolution, which is 20 meters, and the CRS, which is UTM zone 32 north. And at the end, we download the geocoded TIFF file. Let's see if this works. So this is basically the result, and we may see the difference between this visualization, which more or less you can understand a bit, where's the city, where are the mountains, but the geocoded data is much better to actually understand what's going on the ground. So here again we have the city of Bolzano, here we have a river, another river, and the mountains here that are surrounding the city. Basically we can have different visualization. This doesn't work, but anyway, this GeoTIFF here can be used. You can analyze it with different tools, and you can combine it with other sources of data. And this is the important part of geocoding. Okay, then I wanted to show you what we actually created here in the Python client, how does it look like on the, no, it's not this one, sorry. How does it look like on the web editor, so that we have a rough idea on how many blocks we have created with those lines of code, which is something like this. Just a second. So as I was showing, we load the data, we get the coordinate grids, and we perform the multi-loop, which is called aggregate spatial window in OpenEO. Here we are computing the intensity for both bands in this case, so not just for both polarizations, so not just one, but both of them. And at the end, we have the geocode step. Here we are saving as netcf, but it doesn't matter so much. So you may see that defining a common workflow on the Python client creates really complicated workflows. And I want to show you a much more complicated workflow that is being used to compute coherence, interferometric coherence, as Alex was showing you. Since to get interferometric coherence, you have to combine data from different dates, and for each pair, you have to compute the coherence. If you define it in Python, you can just define some recurrent functions that look for the dates and then combine them. But then once you look at the code, it seems impressive because it contains so many steps that you would really have difficulty to write down manually. So relying on an API that allows you to interact with the data so easily, it really helps you a lot to define this kind of complex use cases. Okay, and again, talking about coherence, I wanted to show you a sample result. For example, this was the coherence computed over the province of South Tyrol, the descending track. For the year 2017 in April. And as Alex was saying, you may really see that this would be an urban area, again, the city of Bolzano, and you may see, so the low values are the dark ones, the high values are the lighter ones. That the urban areas have high coherence because they're more or less steady in time, they're not changing. Instead, the rest, the forest, the forest is much less coherent. The fields in the valley, so apple orchards and vineyards, are slightly brighter, so there's a little bit more coherence than in the forest. And this information allows us to apply land cover classification, as Alex was showing, and mapping basically all the classes that we have in our region, which are mostly forest, because it's covered, I don't remember the exact number, but it should be around 80% of the region which is covered by forest, and we just have the urban areas and the crops in the valleys. Okay, let's go back to the notebooks. Just wanted to show you one last thing, which is the radar mask here. So in the region that we are working in, there are many mountains, as you've seen. And since the radar satellite, the Sentinel-1 satellite, is not looking directly from the top, but has this side-looking geometry, there are some areas that, due to the morphology of the terrain, cannot be seen. However, when you get the data, you actually receive some values, but you should also know that this kind of data in those areas shouldn't be, it's not reliable. So you must have a way to generate a mask that tells you, pay attention in this area should be masked out, because in theory, the satellite cannot see it. And we have implemented this procedure also again in OpenEO. And the difference here is that we also use the DM, the digital elevation model, and the local incidence angle. So combining the information of how the terrain, the shape of the terrain with the TM, and how the satellite look at the terrain with the local incidence angle, we can compute a mask, and we can mask out those areas that we have to avoid. I'm not going into all the details here because it's not that complicated, but I think that there are plenty of examples on how to compute radar mask given the local incidence symbol and the DM online. So we basically just reproduce the standard algorithms in OpenEO, but it's a nice feature to have if you want to work with SAR in the SAR domain. Again, here I was creating a batch job, waiting until it was completed. A nice feature here is that you can actually have the same view of the web editor here in Jupyter. So you can actually look at the process that you have created also visually. Just check maybe you did something wrong, you don't understand what was wrong with your pipeline, but maybe due to the order of function that you are calling, there are some mismatch in what you're seeing in the visual version. So this could be also a nice tool to use to debug your workflow. And after that, the process has finished, we downloaded the result, we open it, and at the end we can actually look at our result. For example, this is yet again the city of Bolzano, and you would see that this area here, which is darker, is marked as shadow, and the bright areas here are marked as layover. So those areas should be masked out from the data if we want to perform, for example, a land cover classification, as we also did, because this would improve a lot your training data, and you would also improve your classification accuracy, because you would avoid to put unnecessary noise in your training data. Okay, I think this was enough. So the SAR domain processing, it's huge, and there are so many things that you can do, you can apply, that I think it would be impossible to fit everything in just a simple example. But I hope that this presentation just raised your attention on a topic that maybe it wasn't so interesting for you, and maybe you will check it out through our tools, or maybe through the ESA Snap toolbox, which is always something good to start with. There are plenty of tutorials to start with and YouTube videos. So yeah, I think this is it from my side, and thanks a lot for listening.